Hello students, this is Dr. Ben. I'd like to work out a problem out of the homework from chapter 2. This is part 2 of that assignment, and this is problem 4.22 out of our textbook. And it involves what's called the Atwood machine, which are two objects that are connected together by a string, and they move in the vertical direction. Actually, we studied this problem back in chapter 3, and it was worked out in the textbook, and we also did an example in class. But this time we want to extend our analysis to look at the kinematics of one of the blocks in particular, and it's the one that's on the left in this diagram, the mass that's labeled M2. So we've given some information about the situation. We have the mass of both of the blocks. We're told that they start from rest, and that the second block is originally 140 centimeters above the floor. So I converted that into meters, so we can use it later on, 1.4 meters. And we're asked to find out the time that it takes for that block number 2 to reach the floor. So really this is a two-step problem, because we have to deal with the forces part of the problem first in order to find the acceleration of the system. And then once we find the acceleration, we can use kinematic equations in order to find the time. So in order to do the forces part of the problem, we'll need to apply Newton's second law, because the blocks accelerate as they move. And the tool that we use to do that is a force diagram. So let's go ahead and draw force diagrams for each of the objects. So there's the one on the left, and this dot represents the one on the right. So each of the objects has weight. So there's a downward arrow. Would be M1G, and then the block on the right would be labeled as M2G, and each of the blocks is being held up by the string, so there's tension in that string, and because we really only have one string in this problem, the tension is the same. And just as a check, the tension arrows should be pointing towards each other, which they would as they pass over the top of the pulley. All right, and so I want to go ahead and define a coordinate system for the forces part of the problem. So let's let the positive y direction be up. And then to finish this force diagram, I need to draw the direction of the acceleration of the objects. So mass number 1 is the lighter one, and so it's going to be pulled upwards. So it has an acceleration that is in the upwards direction, and since these objects move as a unit, the acceleration of the one on the right is going to be down. So the value of those two accelerations is the same, but they just point in the opposite direction. And so actually the magnitude of the acceleration on mass number 1 is equal to the magnitude of the acceleration on mass number 2, and I'm just going to call both of those accelerations A, and we'll take the minus signs into account when we apply Newton's second law. All right, so let me move my paper up, and we'll go ahead and apply Newton's second law to this situation. So that's going to tell us that the acceleration is equal to the net force as a vector divided by the mass. So if I apply that to the mass M1, which is the one that's on the left, I would have that plus A, because the acceleration is upwards, would be equal to the quantity T minus M1G divided by M1, and in a similar manner for the mass labeled M2, I would have negative A, because that acceleration points downwards, is equal to T minus M2G divided by M2. So there we have a system of two equations and two unknowns, and I want to find the value of the acceleration, and so I need to eliminate the tension. And so the standard play for doing that is that I take each one of my equations and solve for the variable that I want to eliminate, and then I set those two equations equal to each other. So we have to be systematic about this. So for m1, if I cross multiply, I get a times m1 equals t minus m1g, and so therefore t is equal to a times m1 plus m1g. And I'll put a box around that so we remember to use it. And then if I do the same thing for the mass m2, I cross multiply and I get negative a times m2 equals t minus m2g. And if I solve that for t, I get negative a times m2 plus m2g. And again, I'll put a green box around that equation. And now, if we equate those two equations, because the left-hand sides are the same, the right-hand sides need to be the same. So since t is equal to t, then on the left I would have a m1 plus m1g is equal to negative a m2 plus m2g. And now I just need to do a couple more steps of algebra in order to come up with a relationship for the acceleration. So I'll take all the acceleration terms to the left-hand side and all of the other terms to the right-hand side. So that will give me a times m1 plus a times m2 equals negative m1g plus m2g. And now if I make some brackets, factor out an a on the left, and on the right, oops, my Norton came up there. On the right, I factor out a g and get m2 minus m1. And now I can do one more step in order to solve for the value of a. All right, we'll do that in green. So it's going to be equal to g times m2 minus m1 divided by m2 plus m1. And so we have all the numbers in the problem. The mass 2 is 9.2 kilograms, the mass 1 is 3.6, and if you put those numbers in your calculator, you get 4.3 meters per second squared. So that's equal to the value of the acceleration that now we can use in the actual problem that we want to solve, which is to find the time that it takes for the mass 2 to fall. All right, so part 2 of the problem is going to be kinematics. So we want to find the value of t to f. We want to find out how long does it take the mass number 2 to fall a distance of 1.4 meters. All right, so as we learned in class, the tool that we use to solve a kinematics problem is the pictorial representation. And since the object is of interest is the mass m2, I only need to draw the pictorial representation for that particular one. So we'll draw that pictorial representation. So we'll set that up on a vertical axis that we have labeled as y. And mass number 2 starts at an initial point that is off the ground, and it lands at a final point that is on the ground. And the kinematic variables will be y initial, v initial, t initial, y final, v final, and t final. And between those 2 points, the mass number 2 accelerates downwards. And so that acceleration will be negative in the coordinate system that I have shown because I have the positive direction pointing upwards. All right, so now we can take and make a new list of what we know for the kinematics part of the problem. So the value of y sub I is going to be 1.4 meters. The value of v sub I is 0. The value of t sub I is equal to 0. The value of y sub f is equal to 0. The value of a sub y is going to be negative 4.3 meters per second squared because it points down. And what we want to find for the kinematics part of the problem is the value of t sub f. All right, so move my paper up a little bit and we'll work on this kinematics problem. So we want to find out something about the time. So we want to use one of the kinematic equations that has time in it, but we're not interested in the final velocity. So the first kinematic equation from the list would be the one that is most useful. So that would tell us that y final equals y original plus v original y times t final minus t original plus 1/2 a sub y times t final minus t original quantity squared. And before I do any of the algebra, let's get rid of the terms that we know that are equal to 0. So the value of y final is 0, and the value of the initial velocity of the blocks in the y direction is 0. So that means that this whole second term goes away, and the value of t initial is equal to 0. All right, so we'll make a little more workspace here. So we have 0 equals y sub I plus 1/2 times a sub y times tf squared. So I want to solve this equation for the value of t sub f. So I'll take the second term to the left and make it negative. So negative 1/2 a sub y t sub f squared is equal to yi. Multiply both sides by 2. So I have negative a sub y times t sub f squared equals 2y sub I. All right, have a little more workspace here. Divide both sides by minus a. So t sub f equals squared is equal to y sub I divided by minus a. And then finally we have to take this, we have to take the square root of both sides. So t sub f equals the square root of 2 times y sub I times minus a sub y. And it looks like that number inside the radical might be negative, but it's actually not, because we remember that the acceleration in the y direction is negative in the coordinate system that we picked. So when we plug in the numbers, we would get 2 times 1.4 meters divided by negative 4.3 meters per second squared, and the two negatives cancel each other out, and so if we get our calculator out, that ends up being plus or minus 0.81 seconds, but we need to keep the positive root because we started our experiment at t equals 0, so it doesn't make any sense for time to go backwards. So therefore the final time would be equal to 0.81 seconds. All right, so just to point out again that these two minus signs cancel each other out and give us a positive number inside the square root. And so when we take the square root of a positive number, we get a real number, even though it can have positive and negative roots. All right, so there we go. We had to solve this problem in two different steps. So we had to find the value of a sub y by using forces, and then we had to find the value of t sub f by using kinematics. So the forces gave us the acceleration, and then we were able to use the acceleration in order to find the time. All right, so there you have it, problem 4.22.